Good afternoon, everyone. So, welcome to the week 3 PMRF NPTEL interaction session on structural vibration. So, please can you confirm am I audible and my slides is visible or not? So just write it in the chat box.
Yes.
Yeah, great then. Okay, so my name is Devashish Panda. I am a research scholar and Prime Minister Research Fellow at IIT Guwahati. So for this semester, I have been allotted to this course, Structural Vibration. So this course is actually instructed by Professor Arunashis Chakraborty, IIT Guwahati. And every Saturday, 3 p.m. to 5 p.m. we meet. And what we generally do during this session, we just quickly go through the concept of the current week topics, actually which will directly correlate to the assignments and will help to solve the assignments quickly, relate to the assignments quickly, and when we progress with the course, we will solve different kind of assignments in MATLAB. And after every session, you will get the link of the recording session along with the assignments and notes along with MATLAB scripts whenever we will use the MATLAB. Okay, so today we'll start quickly today's session. So today we will cover the force vibration part. Force vibration, basically force vibration undamped case and also for the damped case. So we will cover both. Okay, then we will go to the dynamic magnification factor. We will spend a few time here because it's a important concept, and then we will move to force transmitted to the foundation and the transmissibility concepts. Okay, so then let's quickly start today's session. And if you go through this video lecture of the interaction session, I hope you will be able to solve all kind of assignments questions. Okay, now force vibration, right? So during the last interaction session, we talked about the free vibration things, right? The free vibration part where we have solved undamped and damped cases. Now in free vibration, we have you know came to know that this oscillation or the vibration is actually generated due to the initial conditions, right? X naught and x dot naught, and it is completely free from the influence of the external dynamic loading. So the response is generated due to the initial conditions, and the structure will be free from the influence of the external loading. Now today we will cover the force vibration part. Force vibration, the structure actually oscillate under the influence of the external loading. So it's actually the vibration is controlled by the external loading. Here you can see F of T is the external dynamic loading, right? Now this external dynamic loading can be of different kinds. Say for example, this Ft can be of harmonic. That means maybe this kind of forces can come, say 10 sine some frequency, say 5t. That means the nature of the force will be harmonic. For example, say for example, we have a structure and one rotating machine is supported by this structure. Now this machine is rotating at a constant rpm, so it will exert an harmonic force to the structure, and the vibration will occur due to this you know harmonic external forces. That can be also cosine terms, also the harmonic forces. Now second kind of forces can be periodic. That means this kind of forces, F naught t, repeat itself after a certain period of time. Say t plus, say period is, say for example, t or t naught. It will repeat itself after a period of time. So for example, for example, like we have a everyone have seen the machine gun, and it has some tripod over it, the bigger machine guns, you know So it has a tripod, and when you pull the trigger, what will happen? One periodic force will come like this, khatak, khatak, khatak. That means you're pulling the trigger and the tripod is experiencing some periodic forces, which actually repeat itself after certain period. So this is T naught. Or there can be different kind of periodic forces maybe there. One example of it can be the tripod of a machine gun, actually, this kind of periodic forces, or can be, different kind of examples can be there, square pulses, then different kind of pulses which actually repeat itself after certain period of time. We will see when we progress with the course. So second is the periodic force, the external. I'm talking about the external dynamic forces. Now third one can be impulse force. Impulse, that means this kind of forces will come for a very short duration of time. So if I want to plot f of t versus t, so it will come a very short duration of time and then it will vanish. It can come at any location, any time point, depend on the nature of the problem. Example of this, that can be the blast loading. Boom, one impulse will come. Or I have to break some structure and one pendulum type of mass, I will hit it. So this kind of thing called the impulse forces. We will see the response of a structure under all these kind of forces. Now, one one another kind of external dynamic forces can be there, that will be random. Random means it is a completely random kind of forces will be there. So we need to look into the amplitude, frequency, and all these things, and go with the analysis. Like random forces, example of the random forces, earthquake force, earthquake, or the wind force. These are the completely random in nature. We don't know which spectrum it will follow or how, what will be the magnitude and all these things. So generally they look like this. If I plot the f of t versus t, so this will look like this, completely random in nature. So we will see the response of the structure under harmonic, under periodic, under impulse, and under random forces, how we can solve it for the damped as well as undamped cases. Okay. So for the force vibration, what we have understood, like the vibration or the oscillation of the structure is generated due to the influence of the external dynamic loading. Now, external dynamic loading can be of these kinds, which we will cover during these courses. Okay. So first, we will see the response of a undamped system under harmonic excitation and for the undamped case, because in the free vibration, we have solved for undamped and damped both the cases. So here also we will solve the undamped and damped both the cases. That means first we are solving the undamped case. That means the damping present in the structure we are considering or we are assuming that is equals to 0. Now, so we will have a basic spring mass system like that. Like one stiffness will be there. Obviously one mass will be there and some external forces acting on it. So this is represented by K, M, and say we are analyzing the structure under the harmonic excitation. So under harmonic excitation, let's say it's a sinusoidal force and the amplitude of force is P naught sine omega bar T. Now here the omega bar or lambda, whatever it is, I will use that omega bar as the forcing frequency. Omega bar is nothing but the forcing frequency. The frequency of the force, not the natural frequency of the structure. Forcing frequency. Okay. Now if we draw the free body diagram of this, what we will get? We will get a spring force will acting along this direction. The value will be kx. If we consider it is a 1 degree of freedom system and the degree of freedom x. So kx will be the spring force. We will have the inertia force which will also act along this direction, mx double dot. and we have the external force which is acting, opposite to these forces. So now we can easily formulate the equation of motion, and the equation of motion will look like mx double dot plus kx is equals to p naught sine omega bar t, right? So here, when we solved the equation of motion for the undamped system, we have this kind of equation: mx double dot plus kx is equals to 0, because we don't have any kind of forces for the free vibration part. So this equation is actually the homogeneous second order differential equation, but here it is a non-homogeneous because we have the forcing part also here. So it is a non-homogeneous differential equation. Now, how to solve this differential equation? It's a mathematical part. Still, we will cover it. So first, to approach or to solve this kind of, non-homogeneous differential equations, we need to have two kind of solutions. Like one is the complementary solution and one is the particular integral. So the complete solution xt will contain two parts. First, the complementary part and the particular integral part. Now, the complementary part actually depends on the natural property of the structure. That means it actually satisfying the homogeneous part, where think about that free vibration case. So it's actually generated due to its natural properties, natural frequencies and all these things and the initial conditions. So xc actually cater to the homogeneous part of this differential equation, and the particular integral actually depends on the force which actually acting on the structure and satisfying the non-homogeneous part of this differential equation. Now, how we can solve this complementary part and particular integral part? So we have already solved the free vibration case, and where we have solved for the homogeneous part, so we can easily take that portion from there. Like the complementary part will become a cos omega n t plus b sin omega n t. Recall when we solved that free vibration case problem, then we got the solution in terms of xt is equals to a cos omega n t, because it scattered the natural properties of the system, and b sin omega t or omega n t, where omega n was the natural frequency of the system, k by m, right? And a and b are the constants which can be easily derived from the initial condition. So here also we have taken this equation, and for the particular integral, what I have just said, the particular integral catered with the force being acted on the system. So here we have a sinusoidal force p naught sine omega bar t. So I'm considering, okay, my trial solution will be x, some magnitude of this force or amplitude of this part into sine omega bar t, where the frequency, forcing frequency is present, because this part actually catered with the non-homogeneous part. Now, if I differentiate with respect to t, I will get this, and double differentiate with respect to t, I will get this. Now put all these values in one, mx double dot plus kx is equals to p naught sine omega bar t. If we put all these things here, so what we will get? Just simplify the equation and just look into here. Substitute values. So we will have minus m omega bar square x plus kx sine omega bar t is equals to p naught sine omega bar t. Now here, from here, I can calculate sine omega bar t and sine omega bar t will cancel out. So x, that means the amplitude will become p naught by k into m omega bar square. Now further, if I want to simplify it, it will become p naught by k, because here 1 minus m by k into omega bar square, m by k under root of k by m, we know omega n square, because omega n is equals to under root of k by n. So it will become 1 by omega n square, and eventually the x, that means the amplitude, become p naught by k divided by 1 minus the forcing frequency square divided by the natural frequency square. That means we have in our amplitude, we have p naught by k. What is that p naught? the initial amplitude of this force divided by 1 minus omega bar square. What is that omega bar? It's nothing but the forcing frequency divided by omega n square. Now, P naught by K, we know it's nothing but the static deflection. So, we can write it down del St divided by 1 minus R square. Now, here R, we are introducing new term here. We call the frequency ratio. Frequency ratio, that means the ratio between the forcing frequency to the natural frequency. Forcing frequency to the natural frequency of the system. So, for this particular integral part, we have solved that x. What will be that x? We have our complementary part here. Now we need to solve for a and b. If we can do this, our solution will come. So here, for the particular integral part, we already solved for the amplitude, which is occurring due to the influence of the external loading, and which comes as xp is equals to x naught sine omega bar t, where I have considered that x naught is the first part. Okay, you can either consider it is x or x naught. So here I am denoted as x naught because it will actually tells me about the dynamic response of this system. Later I will cover it up. So this is the particular integral part. Complementary solution already we have done here. From the free vibration case, we have seen that if damping is not present there, the solution will be look like this: a cos omega nt plus b sin omega nt. So this one is the this one is the complementary part, and this one is the particular integral part. So this is actually the complete solution for the undamped force vibration case, where the forcing function is nothing but a sinusoidal or a harmonic function whose amplitude is P naught, whose forcing frequency is omega naught. Now here, look at this equation. We have A and B. Okay, so we need to solve for A and B. So A and B, how we can solve it for A and B? Because look, this part actually come from the natural properties of the system. That means we can correlate it with the free vibration case, where we can easily calculate A and B from the initial conditions. That means what is the value of x naught initial displacement, what is the value of x dot naught. So let's say initial conditions at t equals to 0, we have the initial displacement x naught and we have the initial velocity x dot naught. Okay, so now using this equation, equation number 5, we will going to use, first we will put t is equals to 0, x t equals to 0, that means displacement, initial displacement is x naught. Now solve for it. So what we will get here in the next slide, we will have x naught is equals to a, or in a way a is equals to x naught. And for the free vibration case also we will get this kind of a and b. Okay, now for calculating b, what we need to do, we need to differentiate this equation with respect to x. That means we need to have x dot of t, that means velocity, because the second initial condition is the velocity at t equals to 0 is x naught 0. Now differentiate it with respect to t. X dot t will become minus a omega n sin omega n t plus b omega n cos omega n t, plus this is the this is the particular integral part. Okay, so substitute these values, we will get p is equals to x naught by omega n minus p naught by k multiplied by omega bar by omega n into 1 by r square. Now put all these values and complete the equation. This equation, put all these values and complete the equation. So we will get the equation like this: xt is equals to a is nothing but x naught cos omega n t plus b value sin omega n t, plus we have this part for the non-homogeneous part of this equation that due to the applied loading. So p naught by k 1 by r square sin omega bar. Now in this equation we have two parts. First part, this is called the transient response of the system, and this is due to the initial condition or the natural properties of the system, and this is the steady state response part, which actually driven by the applied force or the influence of the applied force. Now we will see how the complete solution look like. So what I said, the first part of the equation 7 will give us the sense of the transient response which actually occurred due to the initial conditions. Even what I said, even if there is no initial condition present, still the transient part will be there. Only if vibration, only if damping is there, then this part will die out with time. I will show you the figure. Now what I said, this also can be, this part also can be there due to the natural condition. That means if the initial condition is 0, still we have some transient response for the structure. Like here, if I put x naught equals to 0 and x dot not equals to 0, that means I am not imposing any kind of initial condition, and put all these values in equation 7, what you will get? You will get xt is equals to nothing but p naught by k 1 by r square sine omega bar t minus r sine omega t. That means there will be some transient part present in this vibration, and which actually will decay to 0 if damping is present there. Now if we graphically look into these things, we will see like this. Like that was the forcing frequency or the amplitude of the force. Here this was the force which I have applied to the structure. This is nothing but p naught sine omega bar t. P naught is the amplitude of the force and omega bar is the nothing but the forcing frequency. So we will have two response or two part of the response. One is the transient part. Here you can see, if this is the total response of my system, so it will consist one transient part and one steady state part. Steady state part will look like this, and the transient part will like vary like this. And if damping is present, then it will subsequently died out to 0 like this. So in a, when we are looking for the system where the force forcing frequency is present and the vibration is driven by this external forcing, so there we can have two kind of responses. One is called the transient response, one is called the steady state response. And actually the steady state response we are interested in, because this is actually driven by, if we look this the expression for the steady state response, we find out that it's actually driven by the forcing frequency, and it will last long as the force will attach to the system. Okay, it's not like that. Okay, initial transient part, after the few time, if damping is present, it will vanish it out. But for the steady state response, we will have the constant that response until the force is acting on the system. Now look at the steady state response uh, expression. So it's nothing but, it says xst, that is the static deformation, divided by 1 minus r square. What is r? This is nothing but the frequency ratio omega bar by omega n. And if we have a sinusoidal force, then sine omega bar of t. Now here this part 1 by 1 minus r square. Now this part actually plays a crucial role in the undamped force vibration case. Now look, first if we want to plot it, what will happen? Three cases can be occurred. Like here, there's an important concept, just listen to it. So if we want to plot 1 by 1 minus r square, so r is nothing but my forcing frequency by the natural frequency. So there can be three cases. Either omega bar by omega n should be less than 1. That means your forcing frequency omega bar is less than your natural frequency of the structure. Now if this condition happen, look, 1 by 1 minus r square, this term will become positive because r is less than 1, so obviously we will get a positive value, right? Now if we have the positive value, that means it indicates my xt, that means the response xt and the force pt will be on same phase. That means if my force is acting along this direction, my response will be along this direction along with the force. So this kind of vibrations, when the forcing frequency is less than the natural frequency, we call that in phase vibration. The displacement is called the in phase vibration with the applied force. Now if the opposite will occur, if w omega bar by omega n greater than 1, that means your forcing frequency omega bar is greater than omega n, then obviously this factor will become negative. That means your xt and pt will have negative algebraic sign. That means if the force is applied to that direction, the response will occur at that direction if the forcing frequency is greater than the natural frequency. That means we call this kind of vibration out of phase vibration, because look at the expression for xt. What is that xt? It is nothing but the response, the dynamic response of the system, or the steady state response of the system. Now, and this is the force. So if this part become positive, we will have in phase vibration, and if this part become negative, that means when this part will become positive, when your omega bar is less than your omega n, that means the forcing frequency is less than the natural frequency, and this case will occur when omega bar is greater than omega n. That means in phase and out of phase vibration. Now this actually leads to the important concept which we call the dynamic magnification factor. This RD actually called the dynamic magnification factor, or we can say displacement response factor, or dynamic amplification factor. That means it will tell that how my dynamic response will vary or change with respect to the static response, and we can define the system. So RD for the undamped case, here we are not considering the damping yet. So for the undamped case, RD become 1 by 1 minus R square. Now here also, if we plot the RD versus R curve, that means the dynamic amplification factor versus the frequency ratio curve for the undamped case. Undamped case, that means here your zeta value is equals to 0, or we can say the damping coefficient is 0. So here we can see at when, here also we can have three cases. First, if the W that means R is very less than 1, that means the RD here at the starting point, if R is equals to 0, we will have 1, and then when we move apart from this, here you can see that the response will increase, and again after root 2 the then the response will again fall apart. So here just we have discussed three conditions: when the forcing frequency is greater than the natural frequency, and when the forcing frequency is less than the natural frequency. That just recall that 1 by 1 minus R square curve, you will see that when the in phase and out of phase vibrations will be there. So obviously here we will see the in phase vibration, and here we will see the out of phase vibration. No damping is present. That means at omega is equals to omega bar is equals to omega n, we will have an unbound response. That means the response will be unbounded, but initially it will not be unbounded. After certain time it will get unbounded. Okay, so here from these conditions we can have three cases. First, like the concept of dynamic amplification factor for the undamped system. For the undamped system, xi is not there. That's why we have the unbounded response. When we have xi introduced here, we will see that depend on xi, this dynamic magnification factor will change, because this dynamic magnification factor is important. Why? Because it will tell, due to the applied force, or due to the applied frequency of the force, how that system will react when my values is kind of similar, or greater than 1, greater than 2. That means if we have the natural frequency, if we know what kind of force is acting, what is the forcing frequency, we can say okay, the system is in phase or out of phase, or what will be the dynamic magnification factor value, and subsequently we can calculate the dynamic response and the static response both. Okay, we will solve different kind of examples. For now, just for the concept. So dynamic magnification factor for the undamped system, it's nothing but 1 by 1 minus R square, and R is nothing but the frequency ratio. Okay, so here what I said, that means three cases can be there. First two cases we have discussed. Now if omega bar is equals to omega n, and that becomes 1. So where it become 1, what is happening? 1 by 0, that means infinite, right? So here we will have that dynamic deformation is much more than your static deformation. Okay, and this condition we call resonance. Resonance, that means at that condition where my dynamic magnification factor will be maximum. That means at or when the forcing frequency is equals to the natural frequency of the system, we will have this scenario where dynamic magnification factor become much larger, or we can say that my static deformation is the dynamic deformation is much more than the static deformation, because the response of a system we just express like this: x of t is nothing but we can have like rd term in or here, like, just understand like this: rd is equals to nothing but the dynamic response xt divided by the static response xt naught. Now you can see if rd is large, when the rd become large, or the then obviously your xt, that means the dynamic response, will be much more than your static response. But at that zone where the forcing frequency is less than your natural frequency, we can see that the dynamic the dynamic response is nearly equal to the static response at the at near to the zero, or near to the one part at the very beginning of the curve. Great. Okay. Now what is resonance then? Resonance is nothing but when the dynamic or RD, when the dynamic response factor become larger, or we can say when the forcing frequency matches the natural frequency. Obviously, if you put this R equals to 1 by 1 minus R squared, so you will get what you will get, that infinite. And that condition we call resonance. And in vibration problems, we actually particularly interested in the resonance part, because the maximum, uh, you know, maximum dynamic response is occurring at that condition. So we need to look into that. Okay, at that condition, that's how the structure is behaving. Is there is any kind of parameter which cannot sustain these conditions? So what we need to do, if we impose a higher damping, or if we need to impose higher damping or not, we can decide, and we can correspondingly we can calculate the different situations. Okay, so this was the part for the undamped force vibration case. Now we will go to the damped case, damped force vibration, where damping is present. Now, most importantly, that most of the engineering structures are possess some damping. So obviously, the damped force vibration case will be considered at that situation. Undamped, like damping is not present in any kind of structure. It's like hypothetical kind of things. Okay. So till now, for the undamped force vibration case, do you have any kind of doubts? So you can ask me, or I will move to that damped force vibration case. Okay. So then when we will solve the assignments or the problems, we will discuss more about it. Okay. So for now, damped free force vibration. Now, so for the damped free vibration, what was our xt for the free vibration case? Just recall, e to the power minus zeta omega n t. This is the decaying envelope, right? Multiplied by, we have some a cos omega bar t, or sorry, omega dt. We have defined it damping omega dt plus b sine omega dt. What was that? That was the response for the damped free vibration case. That means we have seen that the response will decay over time, and this decaying envelope is actually dictated by this e to the power xi omega n t, right? Okay. Now, for the force vibration case, where the forcing function or forcing force, like one dynamic force is acting on the system, how the response will change? Because obviously force will be there. That means along with it, we will get some some portion which will actually cater to the force. That means that non-homogeneous part of these equations. That's all. And the solution procedure will be similar. So we will solve one damped force vibration case where also we are imposing the harmonic force, because today we will stick to the harmonic force, and next class we will go to the arbitrary force and arbitrary and your periodic forces along with the impulse forces, how to solve it using the dual and all these things. So today we will stick to the harmonic forces. Now, again, we have a system where damping, mass, and stiffness is present, and one harmonic force is applied to the system. And the amplitude of the harmonic force is nothing but P naught, and the frequency of the force is nothing but omega bar t. This is acting on the system. So I can write down the equation of motion here. Instead of x, I have taken the degree of freedom u. You can consistent with x also, but okay, here I have just done it with u or x. This is nothing but the responses of the degree of freedom I have considered for it. So what will be the equation of motion? Because here spring force is acting there, so obviously we will have the spring action k into x. We have designed this damping as viscous damping, so we are stick with the viscous damping model. In viscous damping model, what is happening? Your damping force Fd is directly proportional to your velocity x dot, or here we have considered the u dot, so u dot, right? And Fd we can directly write c into u dot or x dot, whatever it is. So because we are taking, or we are assuming still now the viscous damping model, so damping force will be that. So obviously we can formulate the equation of motion. So obviously c u dot will acting on that direction, k u will acting is this direction, because I am considering u as the thing, and also the inertia force will acting on this direction, am u double dot, and the force is acting along this direction. Now you can, from the free body diagram, you can easily formulate the equation of motion, and the equation of motion will look like that: mu double dot t plus u dot t plus ku is equals to p naught sine omega bar t. Now let's simplify this equation a little bit. Just divided by mass c by m plus k by m p by m. So we know c by m, what is the, already we have derived that c by m is equals to nothing but twice zeta omega n, right? And k by m is nothing but omega n square. Okay, so we have the equation of motion of the system like this: mu double dot t plus twice zeta omega n u dot t plus omega n square u t is equals to p naught by m sine omega bar t. Now look here again, it's a non-homogeneous differential equation. When we had solved it for the free vibration case, this part was 0, right? Because it was the homogeneous equation, and only the natural properties of the structure will responsible for the motion. So for this solution also, we have a particular integral part and a complementary part, right? So let's solve it. Now for the complementary part, what I said, the complementary part depend on the natural properties of the system. That means we can consider the solution of the undamped free vibration case. That means here we have already derived that on the last class. Xt is equals to e to the power xi omega nt a cos omega dt plus b cos omega dt. Why omega d is nothing but the damped natural frequency of the system, and omega n is the natural frequency of the system. And what is the relation between natural frequency and damped natural frequency? Is nothing but omega d is equals to omega n under root of 1 minus zeta square, right? So the complementary part I will come it later, because the complementary part is already ready. Now we need to solve for the particular integral part. So here for the particular integral part, because the force frequency is present in there, so the trial solution can be of this, like c sine omega bar t plus d cos omega bar t. That means it's nothing but the linear superposition of the harmonics, whatever we have considered. Now again, you just differentiate it with respect to t, and again double differentiate with respect to t, and put all these values in the equation number here 1. So you have u double dot t, you have u dot t, you have ut, all the values, just substitute here. We will have the solution like this. Just simple thing. Just I have just put it all these values here, whatever I have get, and simplify the equation like that. Minus c omega square omega bar square minus d twice j omega bar n plus c omega n square sin omega t plus d. That means I have just broken that separate out these two parts, because next I am going to calculate or compare with the left hand side to right hand side. That means sine to sine, cosine to cosine. So the equation number one, after substituting the value of u dot and u dot p, we have in that format. Now what is happening? Sine omega bar t, and here sine omega bar t also there. So we can equate sine versus sine, cos versus cos. That means this part, first part, is will be equals to p naught by m sine omega bar t. And the second part, as on the right hand side we don't have any cos term, so this part will equals to 0. That means we will have two equations after equating the sine and cosine term on the two part, right? So look, here we have one equation and here you have two equations. Now we can easily solve for c and d. Our main purpose is solve for c and d. So first part and second part. Now first part, if we simplify it little, so c into omega n square minus omega bar square minus twice d xi omega n omega bar p naught by m, right? And for this part, this will be equals to 0. Now from here we can have d is equals to, look, in the second part we have d term, so d is equals to, I have just simplified equation like this, minus twice c zeta omega n omega bar by omega n square minus omega bar square. So I have equation number 4, equation number 5, where c and d is present. Now I need to solve for c and d. How I can do it? Just substitute equation 5, the value of d, in equation number 4 here. Instead of d, just replace the value of the whatever we have calculated. So what we will get, if we substitute it here, we will get this equation here, right? Just put the value of d over here. Look at the d value. So after simplifying, I can get the c is equals to nothing but p naught by k. Just go through it, is self-explanatory and all the steps are written over here. My suggestion is, like, after this class you just written down the derivation. You will see it's like nothing rocket science in between. There is just putting, substituting these values and finding out d and all these things. All these things are done here. Just, and I am not writing it here because it will take a lot of time and we cannot conclude it on time. So that's why the motto is like, we can cover most of the things during that 2 hours. That's all. Okay, so see, once we have found out the c, then put the value of c here, and the equation number 5, you will get the value of d. So d. So I have found out for the particular integral part, what will be the value of c and what will be the value of d. So recall, what was the particular integral part? Up was the c sin omega bar t plus d cos omega bar t. Now replace the value of c and d, you will get the solution for the complementary part. But our final solution ut should be composed of this particular integral part, which actually catered the homogeneous equation, and the complementary integral part, which actually cater for the natural parameter or the natural frequency. That means for the undamped case, for that means the free vibration case. So this part you see t, just recall from the free vibration case, already we have solved and already we have written out the equation, and that was nothing but e to the power xi omega nt a cos omega dt plus b sin omega dt, right? Where omega d is nothing but the damped natural frequency omega n under root of 1 minus zeta square. Now combine these two solutions. So you see the complementary part is there, which actually cater for the natural parameters. That means we can correlate it as the free vibration case, and for the particular integral case we have solved and we get the c and d value. So again, the complete solution, actually, 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 the complementary part, which actually depends on the initial condition and the natural property. And obviously we are solving the damped case. So this transient part here, you can see if this is the total response, we can see if this is the total response. So this total response composed of the transient part like this, because damping is present, so transient part will vanish after time, and only the steady state response will remain to the system like this, unless the force is stopped. Correct? So for the damped vibration case also, we have in the solution, we have some transient part and we have some steady state part. Transient part is due to the initial conditions and the natural property, and steady state part is due to the forcing frequency or the force being acted on the structure due to that. Okay. Now here also, A and B can be found out using the initial conditions for the complementary solution. Just impose the initial conditions, you will get the A and beta. It's nothing rocket science, so you can easily solve it here. So the main thing is, we have seen that for the force vibration case, in solutions we have two kind of solutions. One, that means the final solution actually composed of two things. One is the transient response, one is the steady state response. And the transient response, if damping is present here, the transient response will vanish eventually over time, because for the free vibration case also, we have seen the response will decay over time due to the damping. And the force vibration part, or the vibration, that means non-homogeneous part, the particular integral we have solved, that is called the steady state response. Because this response, the steady state response, this is actually driven by the force being applied on this structure, and the force will be there. So we need to look into, or we should interested to this phenomena of the steady state response. Great. Now here also we can have different scenarios. So like here, mainly if we see the steady state response, so that contains C sine omega bar t and D cos omega bar t. That means the C and D value, whatever we have calculated here. Now look at the C and the D value now. It consists of P naught by K 1 minus R square divided by 1 minus R square whole square plus twice zeta R whole square. What is the R? R is nothing but the frequency ratio omega bar by omega n. Right? C and D. Look, both C and D, the frequency ratio present there along with the damping. Now, three conditions can be also there. If the forcing frequency is equals to the natural frequency, what will happen? Then C becomes, now just calculate the C and D. C become 0 and D become minus P naught by K 1 by twice zeta. And what is that P naught by K? We know this is nothing but the static deformation part, del ST. 1 by twice zeta. Now, for this case, if we have 0 initial condition, we can have the response like this. That means we have a bounded response. That means our response will not get unbounded. Like when we draw that DMF curve for the undamped free vibration case, we have seen that at resonance we have the unbounded response. But here we have seen that at resonance we have the bounded response, and the response will be bounded by P naught by K 1 by twice zeta. And later on we will see that at resonance the RD, that means the dynamic deformation factor, will become maximum, and that value will leads to 1 by twice j, nearly equals to 1 by twice j. Okay. Now look, the steady state response part, we will stick to the steady state response part because we are interested in the dynamic behavior of the structure under that harmonic loading, or under any kind of dynamic loading which is acting on the structure. So that was our for the steady state part, that was our complementary, that was for the particular integral part here. Now these equations I can easily write it down like this. Ut is nothing but this is nothing but the dynamic response or the dynamic deformation into sine omega bar t minus phi, some phase. Right? Now if I write this equation to u0, so what will be the amplitude of the u0? U0 will be nothing but under root of c square plus d square. And phi will be nothing but of tan inverse minus d by c. Already we have solved this equation on the previous two examples. Now what do we know? The definition of RD. RD is nothing but the dynamic deformation to the static deformation, right? Now if we simplify it, so u naught is nothing but under root of c square plus d square divided by ust naught. And what is the ust naught? The static deformation p naught by k. Now if we simplify that, you will get rd is nothing but 1 by 1 minus r square plus twice zeta r third whole square under root. So this becomes the formula for the dynamic magnification factor, or we can say the dynamic, or we can say displacement magnification factor, because here only we are considering displacement. And most importantly, along with the displacement magnification factor, we can have the velocity and acceleration magnification factor also. I will show you how we can get these plots also. So here we have the RD is equals to 1 by under root of 1 minus r squared per whole square. For the undamped case, the RD was nothing but 1 by 1 minus r square. But here you can see we have the damping term present here. That means that we'll actually control the transient part and leads and make it to 0 after time. Okay. So from this equation, if I have the steady state response of a system like this, ut is equals to ut is equals to u naught sine omega bar t minus some phase. Now phase concept you have seen, like when it will be in phase and out of phase. For this case also I will describe when it will be in phase, when it will be out of phase, depending on the r. So u naught, now if I want to write it in the term of rd, so what will be that? Rd multiplied by ust sine omega bar t minus theta or phi, whatever it is. So here for the damped force vibration, the dynamic magnification factor, or more precisely if I want to say, it's the deformation response factor, will be nothing but 1 by 1 minus 1 by under root of 1 minus r square the whole square plus twice zeta r the whole square. Now for the undamped case, we have seen that the dynamic magnification factor become unbounded at resonance. Now for this case what will happen, we will see. So obviously look into the curve. When the first case, when r is very less than 1, that means for this region what will happen, rd will become slightly larger than 1, or we can say 1. That means we can say u naught by ust. That means for this case my dynamic deformation is nearly equals to the static deformation. When rd, or when we can say the frequency ratio omega bar by omega n very less than 1. That means your r is very less than 1, right? There the static deformation is nearly equals to the dynamic deformation. That means the static deformation I can write it down like this, p naught by k. Now look at here, the dynamic response is driven by only stiffness. There is no damping present, or neither the mass is actually influencing the structure. So for these conditions, when the frequency ratio is less than 1, this kind of structures we call the stiffness controlled structures. That means why this is important, like if you have a structure, now if you need to do some dynamic analysis, and if you say and if you want to that ensure that okay, due to that force that structure will not damage. So what will happen, if you see okay, here the forcing frequency is less than the natural frequency, that means the structure is generally controlled by the stiffness. That means we need to look into the stiffness property. Either we can increase, decrease, or whatever we want to do, we need to do with the stiffness things. Okay, so basically when omega bar, that means the forcing frequency is less than omega n, that means slowly varying force, right? Slowly varying force. So for the slowly varying force, the structure actually independent of damping. So short kind of questions may come, like in which scenario the structure is driven by the stiffness only, not the damping. One structure will given to you, a mass, stiffness and damping, all these things, and frequencies will be also there. So if asked, okay, in which scenario the the structure will be driven by or controlled by the only stiffness, not the damping. So here is the case. Now second case, when omega bar by omega n very greater than 1, what will happen? That means the rapidly varying force, the rapidly varying force, that means the force is varying very rapidly. That means out of phase vibration is occurring. That means the phase is opposite to that. That means 180-degree completely, 0 and 180-degree. So here what will happen when this become greater than 1? What will become? Only we have rd equals to 1 by r square, right? Because rd tends to 0, so only we have that r square term. Now if I have the rd equals to 1 by r square, and rd is equals to, we know it's nothing but u naught by ust. So obviously my u naught, that means dynamic response, will become ust by r square. Now if we further simplify, r is nothing but omega bar by omega n, so this term, so p naught by k omega square by omega n square, and further simplify it, p naught by m omega square. Now look, my dynamic response become equals to p naught by m omega square, p naught by m omega square. What is happening here? What is happening here? Omega bar square, this is the forcing frequency, not the natural frequency, it's the forcing frequency. What will happen here? The response is completely controlled by the mass. So if we have, that means that larger mass will attract the higher forces and all these things, the concept will come. That means if we have a rapidly varying force on the structure, we can say, okay, look into the mass and look into the response if all these things are okay, or you need to play with the mass. That means one criteria we have seen, when the forcing frequency is very less than the natural frequency, that means the r tuning ratio or the frequency ratio is less than 1. For this case, we have seen that dynamic response is become nothing but equals to the static response. That means the structure is solely, or the response is solely influenced by the stiffness. And for the second case, when we have seen that omega bar by omega n very greater than 1, the structure is controlled by the mass itself. Now if we want to look into the plot of this deformation response factor versus the tuning ratio, what we will see, that if we increase the damping ratio, the rd value will get reduced. That means my dynamic rd is equals to nothing but your dynamic response divided by static response. Now if rd is higher, what will happen? The dynamic response will be larger than the static response. If this is lower, obviously the dynamic response will be lower than the static response, right? Or nearly at a time. So for a condition where I don't want higher dynamic responses, what we will do? We will impose higher damping ratio. Here we can see, when we increase the damping ratio, here the damping ratio is 0.1, here the damping ratio is 0.2, and here look, the damping ratio is 1. Xi is equals to 1. So we'll have the minimum RD here. That means my dynamic response is less than the static response. That means obviously my structure will be in safe zone, right? And already you have seen, for the slowly varying force, the system will be in phase, and when we will go for the rapidly varying force, the structure will be out of phase to the applied force. So these two conditions. Again, one more conditions will be there. And what will be the conditions? Tell me. we have seen two conditions. One, where the frequency ratio is less than 1, one the frequency ratio is more than 1, and what the most important thing, what that is the resonance conditions, when the forcing frequency is equals to 1. That means the forcing frequency is equals to the natural frequency of the system. That means R equals to 1. So for this case, what will happen? Yeah, the most important thing, what will happen at the resonance? So this condition we call resonance. Now when it is 1, what is becoming the RD? RD will be nothing but 1 by under root of 1 minus R square plus twice zeta R square. What will happen if R is equals to 1? So only we will have RD is equals to 1 by twice theta. That means U naught by UST naught is equals to 1 by twice zeta. That means your U naught will become UST multiplied by 1 by twice zeta. That means UST is nothing but P naught by K, right, into zeta. You can you can simplify it also. Like zeta is nothing but the ratio of the critical damping to the damping present on the system. So CCR divided by C, right? Now CCR is equals to what we know. It depends on the mass and stiffness of the property. That means twice M omega N. So here the 2 will be there because the 2 is here. Now 2 cancel out. What we left out with U naught is equals to P naught by C omega N. Now tell me, at this condition, the response is controlled by what? At resonance, the response is controlled by what? Which parameter of the dynamic system? We have seen the parameter of the dynamic system, mass, stiffness, and damping. So at the resonance, the response is driven by what? Sovik? Obviously damping. At that condition, if we increase the damping, obviously UST will become less, inversely proportional. If we decrease the damping, obviously U naught will be large. So at the resonance, we need to impose the damping properly to get the bounded response or to get the response within the simulated range. So for the dynamic magnification factor, we have seen that three cases can be there. One, when the frequency ratio is very less than 1, that means the slowly varying force. For the slowly varying force, for that condition, we have seen that the structure is actually driven by the stiffness, and the structure will be in phase. That means the phase will be 0. Here for this case, where the frequency ratio is much more than 1, that means the forcing frequency is much more than the natural frequency. That means rapidly varying force is acting on that. And here we have seen that my dynamic response will be driven by the mass itself. Now at the resonance, we have seen, so for this case, obviously the vibration will be out of phase, right? Now at resonance, what we have seen, the structure, the maximum RD occurs at 1 by twice zeta, 1 by twice zeta. And if we simplify it, we can see that U naught is ultimately depend on the C. That means the damping. Here, when 1, we can see from the curve, now you can correlate the curve. Here at that point, we have seen three conditions for this case, for this point, and for this zone. So for here, obviously you have seen the response will be controlled by the damping. That means it will be inversely proportional to the damping. If you increase the damping, you will get less response. If we decrease the damping, you will get higher responses. And at this condition, at the resonance, what will be the phase angle? What will be the phase angle, Bob? 90 degree, the phase angle, because here the phase angle will be at 90 degree. Great. Now, up to this, if you have any questions, you can ask. So this is actually the deformation response spectrum, because here we only considered the U, that means the deformation we have considered, or the X, not we have considered X dot or X double dot. So we can have two other deformation response factor curve. First one is the velocity deformation response spectrum. Velocity. So how we can get this spectrum, or how we can get this curve? Just quickly I will tell. So we know ut already you have derived. Okay, the steady state response of a system ut or xt is nothing but u naught, that is the dynamic response of the system, sine, if the sinusoidal force is acting there, omega bar t minus phi. And what we know from the rd is nothing but u naught, the dynamic deformation, by ust naught. So if we simplify it, you will get ut, the response or the steady state response, is nothing but rd ust naught sine omega bar t minus phi. Right? Now, if you differentiate it, what will get? This. Now, divide both sides by omega n. What will get? Just simplifying it. I'm just simplifying it to get, in terms of velocity. So wn, if we divide by wn, what will happen? U naught by, just I am taking this on this other side, p naught by k omega n. So rd by omega n, omega bar cos omega bar t minus phi. Now just simplify it. What will I get? Omega naught by p naught by k omega n rd r cos omega bar t. Now ultimately what I will get, that rd here, so after simplifying the rv, here it is written. Just go through the steps, you will easily understand. rv is nothing but I will get r, that means omega bar by omega n into rd. So the velocity deformation curve will be r times, that means the frequency ratio times the rd, that means the deformation response curve. Now at rv is equals to 0, when that rv is equals to 0, rv is equals to 0 when r equals to 0. That means it will start from the origin, not from here 1. For the dynamic deformation curve, we have seen that the curve is starting from the 1. Why 1? Because rd is nothing but 1 by 1 minus r square twice zeta r. If r equals to, you know, if zeta also and r also become 1, it will get the value of 1. But here what we see, that if r value is 0, then obviously the total rv will become 0. Okay, so here we can conclude three things. Obviously it will also vary with the damping. So rv 0 at here at the beginning, rb is maximum at here when w, that means the forcing frequency is equals to the natural frequency, and rd tends to 0 when that frequency ratio approaches infinity. Now again similarly we can have the dynamic magnification factor curve for the acceleration also, and for the acceleration similar kind of derivations is there. You just look into the derivations, like we already have the steady state response of displacement. Then after double differentiating, I am getting this, and finally the ra become r square into rd. So obviously, or we can say that ra by r is equals to rv is equals to r. That means rv is equals to rd. So this is the velocity response, this is the acceleration response, and rd, this is the deformation response. And what is the value is that 1 minus r square whole square plus twice zeta r whole square. Now obviously r term is sitting here. So when r is get equals to 0, obviously my ra value will be equals to 0. That means this plot will also start from the origin, not from the 1 point. only the RD, that value, the deformation response curve will start from the 1 value. Okay, because if we put R is equals to 0 in the displacement response curve, what will happen? You will get 0 0 RD equals to 0. Sorry, 1, RD equals to 1. So only and only the dynamic deformation curve for the displacement will start from the 1. Other two plots for the velocity, because the velocity RV we have derived is nothing but R into RD. That means if RD is given, you can, if one question asks like calculate the velocity response factor for this thing, so you just need to multiply R. The frequency ratio also given will be given to them there, and RD already you can calculate from the 1 by under root of 1 minus R square plus twice zeta R whole square thing. So these are the three different kind of dynamic magnification factor. Dynamic magnification factor for displacement, dynamic magnification factor for velocity, dynamic magnification factor for the accelerations. So now you have you have some little bit of understanding about how we can use the dynamic magnification factor to identify different kind of structure, to different kind of scenarios, or to categorize different kind of responses. Like for the slowly varying forces, what will be the responses? For the rapidly varying force, what will be the responses? At the resonance, what will be the responses? And all these things, right? So that was the that was all about the force, vibration and dynamic magnification factor. So we have two more topic, little bit of small topics are there, then we will move to our problem solving sessions. So first thing, so till now, do you have any kind of questions? Now we will solve different kind of problems. We have different lot of problems here. We will solve one by one. So till now, do you have any kind of questions? If not, then we move to like half power bandwidth method. What is that method says? Using that half power bandwidth, we can actually calculate the damping value for a damped force vibration. Like for the undamped free vibration case, we had that logarithmic decrement. From the logarithmic decrement plot and from the cycle of the response, we can easily calculate the damping value. We have seen. Now for the force vibration case also, we can find out the damping value. So but here, like, this method is not that much popular. This method is only applicable for SDF system and for small values of zeta. That means if you have zeta 0 less than 0.02, that method will converge. Otherwise this method will no of use. Now how this method actually tells about the you know damping. So first thing, tell me, if we have a signal or response x of t, what will be the power or energy of the signal? Nothing but you just integrate the signal square over the domain. You will get the energy. And how we can get the power? For one cycle, if you integrate this, you will get the power. Now, here for this concept, actually it says ki if we have, so this is the frequency where we have the maximum peak. So here we are considering the single digraph freedom system, so obviously we will have one peak. So this is the maximum amplitude or maximum RD. So we need to down for the point, so where the power will be half, and this point is actually achieved by RD divided by under root of 2. Now, once we reach to the half power point, we need to identify the two frequencies of either side of these two power points. That means obviously we are doing it in the frequency domain calculations, and bandwidth, that means band of the frequency. So here if this frequency is WA and this frequency is WB and this middle frequency where the maximum amplitude is occurring, if this is omega n, so the half power bandwidth method says the zeta will be equals to WB minus WA divided by twice omega n. Or if we have the cyclic frequency, so zeta will be nothing but FB minus FA divided by twice Fn. By this way, we can calculate the zeta value from the half power bandwidth method. Now we can like here I have written it down like zeta is equals to WB minus W divided by twice omega n. We can also prove this thing. Like here already we have seen that RD very simply, RD is nothing but 1 by 1 minus r square plus twice zeta r. Now at resonance, what will happen? R is equals to 1. That means RD becomes 1 by twice. That means this is the maximum RD, right? 1 by twice zeta. So obviously your X max will be XST into RD. So this will be that. Now for half power, what do we know? This RD part, we need to equate with to the this part, that means XST by twice J and 1 by root 2. Because for the half power, it says that the half power will be reached, up to root 2 of the maximum deformations. Now, if you solve it, what you will get? You will get like this kind of equations, and if you solve it, you will get R1 and R2. R1 and R2 is nothing but if we are considering the curve as per the frequency ratio R. If we draw the ordinate R here, so this will be nothing but R1 and this will be nothing but R2. Now here we can see that it become zeta ultimately become, it's nothing but R1 minus R2 or R2 minus R1 by 2. Now R, we know R means is nothing but omega by omega n or omega bar by omega n. So R1 will be omega 1 by omega n and R2 will be omega 2 bar by omega n. Now if you simplify it, you will get zeta is equals to omega 2 minus omega 1 by omega n, right? Now one more case is there. If the natural frequency is not provided, and crudely we can approximate if only the two frequencies are provided on the other side, here and here, only the two frequencies are provided, nothing else are provided. So for this case, we can approximate the zeta is equals to nothing but your lambda 1 or omega 1 minus omega 2 divided by omega 1 plus omega 2. It's the crude approximation of things. But if in a question asked where the frequencies are, the natural frequency or the forcing frequency at which the maximum displacement is occurring, if this is not provided in the question, then you can approach this question like this and solve this question. Great. Okay, now let's solve a few questions. So till now, do you have any kind of doubts? What we have covered, like what will be the response for force vibration for the undamped case? What will be the and what will be the dynamic magnification factor for the undamped case? Undamped case, the dynamic magnification factor only depend on the frequency ratio, not on xi, because the damping was not present there. So only the 1 by 1 minus r square term was there and all these things. Then we have solved the damped force frequency or damped force vibration case, where we have seen again we have two parts, transient part and steady state part, and steady state part actually of our interest, and we have seen that okay, how to calculate the RD value. Along with RD value, we have seen different kind of scenarios in RD curve, where we have seen for the slowly varying force, for the rapidly varying force, and at the resonance conditions. Also we have derived the deformation response for velocity, deformation response for accelerations and all these things, and also little bit talk about the half power bandwidth. Now let's quickly solve few examples and then we move to the support motion and solve other examples. Okay, so here the first questions, pay attention please. A harmonic force Ft is represented by 25 sine 20t is acting on an undamped, look, undamped SDOF system having a natural frequency 3.5 hertz. The undamped natural frequency is given is 3.5 hertz. Calculate the dynamic magnification factor for the system. Okay, so the forcing frequency, the force is given here, f of t is equals to 25 sine 20t. So what is that 25? This is the amplitude of the force. What is the frequency of the force? This is the frequency of the force. So lambda or omega bar is 20. Great. What is the natural frequency? Omega n. Omega n is given as 3.5 hertz, the cyclic frequency. So we need to calculate it in the circular frequency term. So twice pi f. That means it comes as 21.99 rad per second. Now once we have two ratios, so lambda it's nothing but it's also in rad per second. So lambda is nothing but, or omega bar is nothing but 20 rad per second. Now look, what will be the frequency ratio? R is nothing but omega bar by omega n. So we have all these things 0 point, and I'll put all these things. Omega bar is 20 divided by 21.99 and it comes as 0.909. Please check the calculations once again. So what will be the magnification factor RD for the undamped system? It's nothing but 1 by 1 minus R squared. Just put all these values and check the calculations and it will come as 5.756. Great. Now move to the second question. So this question, do you have any kind of doubts? Is it? Okay. So move to the next question. A structure modeled as damped spring mass system with weight 12 kilonewton, stiffness 10 to the power 3 kilonewton per meter, and damping is 22 into 10 to the power 3 Newton second per meter. Is subjected to a harmonic excited force 25 sine 35t. Calculate the maximum dynamic magnification factor for the system. Maximum. Now tell me, maximum dynamic magnification factor occur when omega bar is equals to omega n. That means the forcing frequency matches to the natural frequency, right? So directly either we can say already we have solved it that RD value at resonance is nothing but twice zeta. So without calculating this, if you have the zeta value, you can easily calculate it like 1 by 2 into zeta. Zeta means it's nothing but the ratio of C by C CR, the damping and the critical damping. Now how you can calculate the critical damping CCR? We have the formula twice m omega n. So from here we can get the value of CCR and the CCR value. The critical damping value is coming as that. Now damping ratio we can calculate. Already C is given, so CCR is nothing but this. So it comes as this, and just put it in the value like 1 by twice zeta, because at the resonance we have seen the maximum dynamic magnification factor is 1 by twice zeta. Now you don't need to consider this part because this will contribute very less. So twice into zeta will give you 7.11 or 1/4 answer. So the answer will be within that range. Great. Now move to the next question. Yeah, the half power bandwidth. In your assignment, I have seen it. That's why I have told you that. So here the forcing that the natural frequency is not provided. Only two frequencies are provided on the two sides. So obviously, what you need to do while calculating the eta is nothing but lambda 2 minus lambda 1 by lambda 2 plus lambda 1, and it will lead to 0.0909. Okay, this will be the correct answer. Now, the fourth question. Yeah, I also have seen this question, but just for your purposes, I have put it here. The damping ratio of an SDF system is found as 7%. Calculate the specific damping capacity and the specific damping factor. So till I have not covered these things, but the question is there, so I must discuss. So damping ratio is 7%. So the specific damping capacity actually calculated using this formula 4 pi eta under root of 1 minus eta square. We will see when dedicatedly when we will go through the damping module. I will cover these things. So for now, solving this question, you just need to solve like this, and the specific damping factor is nothing but the specific damping capacity divided by twice pi, and it will lead to 0.14. Right. We have many more example left, but we have one more topic left. I just missed it out, like force transmission and vibration isolation. How much force is transmitted to the foundation, and what we call the transmissibility concept, because 3 and 4 questions will come from the transmissibility part, and we have the questions here. So to solve them we just need to go through this concept little bit, just for 2 or 3 minutes, we will cover this portion and we will solve the rest of the questions later. Okay, so force transmission and vibration and isolations, very important. Like if a structure is supported on a foundation and one harmonic force is acting on it, so how much force is getting transferred to the foundation? Because when we will design the foundation, we need to uh, think of the forces which may come to the foundation, and if this force will exceed the tolerance limit of the structure, then obviously the force or the structure may fail. So for these conditions, how we can see how much force is transmitted to the foundation and all these things. So for this case, we just consider a single spring mass damper system which is resting on a foundation, and one harmonic force p naught sine omega bar t is acting over the system. So obviously ft will be the force which will be transferred to the foundation. So ft will consist nothing but the spring force k into u of t and the damping force, because we here we have considered the viscous damping part, so c into u dot t, right? So this much of force will be transferred to the foundation. Now let's try to find out the magnitude of the force. So before finding out the magnitude of the force, what we need to do, we need to have some solution of this force so that we can easily calculate the magnitude. So what will be the solution of this? Is nothing but this can be written as a you know uh, mm, steady state response u naught sine omega bar t minus phi. So now differentiate with respect to t and put all these values here in this equation. So the ft is become or coming as ust multiplied by rd in bracket k sine omega bar t minus phi plus c omega bar cos omega bar t minus phi. We will get the equation after substituting this in here. U naught, we know what is U naught, because RD, now we have the concept of RD is nothing but U naught is the dynamic response divided by the static response. Okay, now I can easily, from the equation number 3, I can easily calculate the amplitude of the force transferred to the foundation ft naught value, and it will be nothing but the constant term here ust into rd multiplied by under root of a square plus b square. That means a is nothing but the k and b is nothing but c omega bar, right? Now this is the amplitude of force getting transferred to the foundation. Now let's simplify it further. Now this is the force which actually get transferred to the foundation ft naught. Now let's simplify it. ust into rd, ust we know static deformation p naught by k multiplied by rd, and from the under root I am taking k out, so it become 1 plus c omega bar square divided by k the whole square, right? Now we know that zeta is equals to nothing but c by ccr, or we can write c by twice m omega n, and omega n is nothing but square root of k by m. So ultimately my ft naught become p naught rd, because only k and k will be cancel out, p naught rd will be there, p naught rd under root of 1 plus, here I have simplified that c is equals to nothing but twice times zeta m omega n, that is only written here twice time m zeta omega n and omega bar divided by k the whole square. Now we know that omega bar by omega n is nothing but r, and here under root of k by m is nothing but omega n. So here in the denominator part I will have omega n square. So 1 omega n cancel out, 1 omega bar by omega n will be there, and by there the r term is getting. So the amplitude of force getting transferred to the base or the foundation will equals to p naught rd under root of 1 plus twice zeta r square. That much of force is getting transferred to the foundation. Now the transmissibility TR actually is the ratio of the amplitude of force getting transferred to the foundation. That means what we have just calculated ft naught divided by the amplitude of force applied. What is the amplitude of force applied here? P naught. What is the amplitude of force getting transferred to there? ft naught, because ft naught we have calculated here. So this ratio is called the transmissibility, and it is very important concept, because when we will design some foundation or some structure which actually contain different kind of vibrating systems, for there we need to know how to isolate the base, right? So ultimately the transmissibility ratio TR, the formula of the transmissibility ratio becomes 1 plus twice zeta r the whole square divided by 1 plus r square whole square plus twice zeta r whole square under root. That means it's nothing but RD multiplied by your this term 1 plus twice zeta r the whole square and total under root. So this is called the transmissibility. The ratio of the force transmitted, this one is the amplitude of force transmitted to the foundation, and this is the amplitude of force applied to the system. Now if I draw the transmissibility versus frequency response frequency ratio plot, because in the transmissibility equation we have zeta and r. Zeta, that means the damping ratio, how much damping present in that structure, divided by r. Now if we plot it, what we will see, that tr at the initial part the tr will equals to 1, and then at the resonance frequency it will get the maximum value will be transferred, and after root 2 again the tr will be become 1 and it will reduce. So after that root 2 we can assure that okay, for the higher values of damping we will have less transmissibility, and for the lesser value of damping we will have the higher transmissibility, because if we put the root 2 in the TR equation you will get that it will become 1 at the value of root 2. So here after root 2 it depends on the xi zeta, and here at the resonance it also depend on zeta, but maximum amount of force, that means the magnitude of your f t naught will be maximum, the maximum amount of force will be transferred to there. So for the vibration isolation things we need to consider okay, how much damping should be there, how to cross that root 2 part and all these things. So that actually associated with the transmissibility, but transmissibility is a huge chapter. Within that 5 or 10 minutes it cannot be covered, but till now just for the assignment purpose we have solved that how much or what will be the amplitude of force getting transferred, this equation. Without this equation you cannot solve to I think one question. And we have seen that the transmissibility versus r curve and the formula for this thing. Okay, now let's solve our assignments. We'll see these also they are the equation of motion under ground motion. If I time then I will explain these things. So before that just let's quickly go through the examples. Okay, here look, a machine of mass 100 kg is supported on a spring type isolator with a total stiffness 75 kilonewton per meter and a damping ratio 5%. The operating frequency of the machine is also given 3.5 hertz. Calculate the transmissibility ratio. Now you know what is the formula for the transmissibility ratio. It's nothing but 1 plus twice r eta or zeta. Zeta and eta both used for the to represent the damping, divided by 1 minus r square twice eta r whole square. So what we need to calculate? We need to calculate r is nothing but omega bar by omega n. What we need to calculate? We need to calculate the value of zeta. So do we have the values here? Yeah. Mass and stiffness are there. So I can calculate the omega n, the natural frequency, which comes as 27.39 rad per second. What is the forcing frequency? Forcing frequency is given in terms of cyclic frequency. That means F term. So we need to convert it into omega. Omega is equals to nothing but twice pi F. Omega is the circular frequency, natural circular frequency. F is the cyclic frequency, number of cycle per second. So twice pi F, and it gives us 21.99 radian. So what will be the frequency ratio? Frequency ratio will nothing but that omega bar by omega n. It comes as 0.8. What will be the TR? Just put all these values, because we know the damping ratio zeta is given as 0.05 in the question itself. So please check the calculation and tell me you are getting 2.72 or not. Just do the calculation quickly. Are you doing it? Or I will move to the next question. Savik? Okay, then let's solve the next question. Yeah.
Yes.
Yeah. So, have you checked it? It's coming as 2.72. Just if you have calculator, just check it. Divided by 0.136. 0.1.
Yes, it's correct.
Yeah, we are getting it. Okay. Then you need to choose the range correctly. Okay. For your assignments. Now, next question is support motion of 0.6 sine 20 omega t is induced to an SDF system having a mass of 85 kg, stiffness 65 kg, and damping ratio is 8%. Calculate the amplitude of force uh, induced. That means the amplitude of force getting transferred. That means what we have calculated here. That's why this thing is important. What I said, this F T naught is equals to P naught RD 1 plus twice zeta R. Using that equation, we are going to solve the question. Without that, it cannot be solved. So let's see. What do we need to find out? Omega n from the system's mass and damping. So omega n is nothing but this. Lambda here 20 omega t is given. That means generally like P naught, the forces are represented like this sine omega bar. It's in terms of the circular frequency, not the cyclic frequency. And in a question, if specifically mentioned in hertz, then you need to convert it to that circular frequency minus 5 or plus 5 like that. Okay. So we have the forcing frequency, we have the frequency ratio. Now, what is the amplitude of force getting transferred? We have just solved F T naught or F naught is nothing but P naught into RD under root of 1 plus twice zeta R square. Now, if we simplify it, P naught into what is the RD value? What is the RD value? Is nothing but X naught by XST naught multiplied by under root of, just pay attention, plus twice zeta R the whole square. Now, if we simplify it again, P naught multiplied by X naught divided by what is that static deformation part says? Static deformation part is nothing but P naught by K under root of 1 plus twice zeta R the square. Now P naught and P naught cancel out and we left out with this formula. F naught is equals to X naught, the amplitude of the force, K under root of 1 plus twice zeta R the square. Now we have all the values. 0.06 is the amplitude of force here. It is provided. 65 is the K stiffness. Under root of R already we have provided 0.72 and the value of eta or zeta is given as 8%. That means 0.08 and the value is coming as 3.926. Understood the question? How to approach it? Yes or no? You are not interacting. From the next class and onward, I will not put that kind of question. I will put the different kind of question. You need to solve each and everything by yourself.
No, it's fine.
Yeah. Okay. No, you need to like. It's feeling like I'm talking to the screen itself. Yeah, it's okay.
No. We are following. This is a more or less like a very difficult section.
Yeah,
So
that's
you are
why.
not trying to understand
Yeah, that's
what
why
you are
I need to
teaching,
pay
and
attention.
then
Otherwise, neither you can solve the assignments nor you can solve the questions in the final exam.
exactly.
Exactly.
So exactly, we
And
appreciate.
like also this, I cannot solve the direct questions, similar kind of questions. So this is the similar kind of question you can correlate. but you need to understand how to solve it. Otherwise, what is the induced effective force? You will scratch your head all the day long, है ना? Okay, no issue. Now the next question. An SDOF system is excited by an harmonic force. The amplitude at resonance was measured equal to 3 centimeter. Look, amplitude at resonance is 3 centimeter and equal to zero point 0.2 semi at 1/10 of the natural frequency of the system. It is one of the toughest question. Like GATE will also not ask this kind of question. Okay, no issue. We will solve it. Natural frequency of the system. Estimate the damping percentage of the system. Great. कैसे निकाले? How we can find it out? So due to the harmonic force, we know what will be the deformation. It's nothing but y is equals to nothing but your RD into UST. So we can write it like U static part or X static part divided by your that part 1 minus R square, R whole square plus twice zeta omega n whole square. Now look what it says at resonance, that means lambda equals to omega n or omega bar is equals to omega n. Lambda actually used by your course instructor and I generally use the omega bar as forcing frequency. Okay, so these two notations similar kind of things, and eta is actually used by your for your instructor for the damping, and I generally use zeta for it. So these two notations are for same things. Okay, so now using this expression we need to solve the example. So at resonance, what will be the value of y? We have already seen is nothing but the static deformation divided by, just put it lambda is equals to omega n, we will get this f naught by k divided by 4 eta square. That means 3. Here they have provided at resonance the displacement is equals to 3. So we can write it like this 3. Yeah, Sovik, you want to say something? Your mic is on. Oh, okay, no issue. Okay, so 3 is equals to f naught by k 4 eta square, right? Now, what they say, the same response will be 0.2 centimeter at 1/10 of the natural frequency of the system. That means when the forcing frequency will be equals to Wn by 10, at that scenario, the amplitude will be 0.2. So for the first case, we have seen 3 is equals to nothing but f naught by k 4 eta square, because for this condition my resonance will occur, that means lambda will be equals to omega. Now for the second case, the y will be 0.2, that means for the omega n by 10 case. So just replace these things and put here, you will get like this. Now what you will do, you will two equations, equation number 1 and equation number 2. This is not the equation number 1. So this is equation number 1, this is equation number 2. What you will do, just divide equation number 1 divided by equation number 2 and equate it. You will get the eta. Eta is equals to nothing but 0.0328. Just check the calculations. By the solution procedure will be same. That means the eta will come as 3.28%. Okay, 3.28% to 3.3%. All these things. Get it? How to solve it? We are solving is using that dynamic magnification factor or the the displacement whatever we are getting at the resonance from these things. Clear? Now we have another
Sir,
some.
sir, one minute. In previous question, answer 3.28 it is written. A percentage is not written. Without percentage, that answer is correct or not?
I haven't seen the your options. Now here eta is coming as 0.0328. Either they can ask as a percentage or
Can you
just
see the question? Can you?
kindly. I don't have the access. Can you send me the question, then I can say it. Okay. What they have asked, with percentage or without percentage?
No,
Yeah,
actually, question is asked, but nothing is told about what is the ratio. It is told.
estimate the damping of the system. In
Yes,
bracket,
yes.
I think the percentage will be there. If it is not the MCQ type of question, the percentage will be there. If it is a MCQ type of question, you can directly put 0.328 if the question is there. If it is not MCQ type of question, if you have the question, I think like this in percentage term in bracket they will mention either in percentage or in just in digit.
Okay, okay. I will share the question, sir.
Yeah, no issue. You just share the question, I will submit. Like it is simple. If you have the eta value like this, let's look for the what type of question is that? Is it a multiple type of question or it is just actually
Multiple
the
choice question, sir. Multiple choice question.
multiple type of question? And what were the answers were there?
3.28 was the answer, sir. There was no percentage was in the answer.
No
Option of
percentage.
percentage was not there.
No. In the question, just look into the you have the question.
Okay, I will share that screenshot, sir.
No. Don't need to share it. Just read it out. The question, full
Okay,
question.
one minute, one
Read it.
minute, one minute. Let me go. This is in what two.
Estimate the last line. Only read it out the last line.
1 minute, 1 minute. Let me open that question.
Yeah, no issue. But I hope you understood how to approach this question.
The question is for a viscous damped single degree of freedom system. It is observed that the amplitude of free vibration decreases from 1 to zero point 0.5 at third cycle. Select the correct statements.
Cycles. It's, I think you are seeing the wrong assignments. Cycles, that means it's free vibration case, right? We have solved in the previous day. It's the force vibration case. It's your assignment 3.
No, this is assignment 2, sir. Week 2 question, question number 11.
But we are actually discussing assignment 3. This is the week 3.
Oh, sorry then.
Yeah, week 2 already we have discussed on the last class. You have the last video lecture, you can see it.
Okay, then this doubt, can you clarify me
Yeah,
this
yeah.
doubt? Sir?
Obviously, what was your doubt? Tell me, I just clarify it. If it is in percentage, you need to put it in percentage. If it is not there, you need to put it in like the digit value. I think these assignments already get evaluated, right?
Okay, I will see then. I will discuss in the
If
next class.
yeah.
Okay.
Or you
Yes,
can
yes,
mail me. I will
yes. The assignment two is evaluated already.
yeah evaluated. Bob, can you correlate the question? What he's trying to say? Which what question is that? I think we have already discussed it on that last class.
Yes, that one is gone. This is for assignment three.
Yeah.
Sir, here answer is also solved and it is told damping ratio of the system is 3.68, but damping ratio should be less than 1. No?
In percentage it can be 3.6%, but in if it is not in percentage, then obviously it will be less than 100%. Cannot be na.
Yes, but here in answer also written
Written what? One sec. You, I need to I just finish today's class, then I will get back to you. What is your doubt?
Okay,
After
okay,
the
okay,
class, just
fine, fine. Sorry.
be here after the class.
Yeah,
Just after the class, we are solving. We go back to that question and we will see.
okay. Sorry for the disturbance.
Yeah, no. This class is for your clearances only. But we are solving assignment 3 questions today. Anyway, okay. So we have the rotating machine. Look, a rotating machine having a total mass of 200 kg is supported by 4 isolations on rigid floor. The total stiffness of the isolator is given 1000 into 10 to the cube Newton per meter. When operating this machine, generating an harmonic force of amplitude 450, the amplitude of the harmonic force is given at rotational frequency of 50 hertz, assuming zeta is 0.2. Check the amplitude of the motion does not exceed the allowable amplitude is 0.3. Okay, great. What we need to do, we need to calculate the amplitude of force which is getting transferred, and we need to check the amplitude is not excess the allowable amplitude of the force. It's similar kind of things. First we need to calculate the natural frequency. Already the forcing frequency is given, so here the forcing frequency is given 50 hertz. So we can have the natural frequency first, then we convert it into hertz, and the frequency ratio I have calculated. Once the frequency ratio is calculated, we can easily calculate the RD value, dynamic response factor. And once the dynamic response factor is completed, we can calculate the value actually the displacement amplitude produced due to that RD, because we know U naught is equals to P naught by K into RD. So RD value comes as 0.353. So U naught will be 0.0329, and which is less than equals to 0.03 mm. So okay, it is the it is within the safe limit. And here also same thing are provided, like what will be the value of transmissibility and what will be the value of force transmitted to the foundation. And force transmitted to the foundation, if you know the F naught, you can multiply it with TR and you can get the value of FT. So it's a very simple and straightforward question. Just look into it, you will get the solutions. I have another kind of question.
Hello.
Yeah,
Yeah.
yeah,
How
please.
are you able to clearly identify the forcing frequency and the natural frequency so easily, even if it's not clearly stated in the question?
Yeah, here. First thing, the forcing frequency is given as 50 hertz itself in the question. What is the natural frequency? The mass of the system is given as 200 kg. The stiffness of the system is given as this. Can I calculate the omega n, Bob? All the steps are written over here. Just look into it, you will get the solution. Clear?
Yeah.
Yeah. Great.
Okay.
Yeah,
Because
yes,
this
sir.
was stating a rotation of 50 hertz, and then so the rotations are the the forcing frequency. Not
The
the case.
rotational frequency of 50 hertz. The rotational frequency itself in the question is provided the rotational frequency. Obviously, the rotational frequency is coming from the force itself. That means the forcing frequency. If this term is there, that
Okay.
means you need to correlate with the forcing frequency term, right? So get it how
Okay. Okay.
yeah. Okay. One more thing. This example is very simple and straightforward. Just go with that. You will get it, like transmissibility thing. Now, be careful with the MSQs. There might be two kind of answers, so you need to put two as a correct answer, otherwise you will get zero. So here, just for your purpose, I have put few questions here, like the transient response of a SDF system due to force vibration depends on, we have discussed many times today, what the initial displacement, initial velocity, that means the initial conditions. So A, B both will be there. The transmissibility ratio will be one for which frequency ratio? Tell me, transmissibility ratio or value will be 1 for which cases? We have seen two cases, when r equals to 0 and when r equals to root 2, A and C. Great. So two answer will be correct. Here, like let the natural frequency of an SDF system and the forcing frequency are omega and lambda. When the resonance will occur? Obviously, when the forcing frequency will equal to the natural frequency. So correct answer will be B. How energy dissipated in one cycle due to the viscous damping? Many times we have decided like it's depends on the uh, amplitude of the structure, or more precisely your velocity of the structure. That means here the velocity is not written, so we need to correlate with the amplitude. That means ED is directly proportional to the amplitude square. So okay, so this one is for today. Now let's quickly see what is the problem of him. Okay, then I'm not sharing this screen, and just discuss what was the question and what was the problem regarding the last class. Okay, so today's class, I think if you watch the video, you can able to solve all kind of questions. I have address all kind of critical questions for these assignments. So but you need to be careful, because it's not like that codes you can easily without practicing you can solve all these things. You don't expect this kind of scenarios, so you need to practice a lot of questions. After that you can able to solve all kind of questions. Now you can see that questions from where to start and for why to be what to how to get the answers, all these things. So let's see this
Sir,
problem.
here I want to talk something, sir. Questions, no questions. This type of questions, from where we can get any book or any selected question. Can you also share with us so that we can practice?
Selected question. I have suggested you one book, the R.K. Chopra. There are many questions are there. You can practice them. It will get you the complete idea. No issue.
Okay, sir. Okay, thank you.
Okay, or just go through the video lectures, whatever your course instructor have covered during the course. Also have covered this example first, then I have discussed different kind of examples so that your assignment solution, um, you can easily solve the assignments and you can submit it. Uh,
Yeah, yeah, yeah. Okay, sir.
now
Okay,
your
thank you.
question, like
Uh,
what was like, I just forgot, but let's share the previous days uh, PPT, then we can find it out, right? It's like, completing the full content along with the questions within 2 hours is little difficult. That's why, uh, you know, that kind of rapidness, and I need to write it in a copy, and after that I need to, describe you. Okay, you are presenting the screen, right? You present it. Let me see what is the problem, or what is the problem. Yeah, please share. Are you sharing? Bob, can you recall the question? What was that question? I cannot recall. Actually, percentage or the yeah,
sir, I will read the question.
yeah. Just zoom in. I cannot see it actually. Yeah,
Uh, Now this is the 11th question for a
yeah.
viscous
11th
dam.
question. Just you just need to zoom out little bit. Yeah, 1 to 5th cycle. Select the correct statement. Yeah, correct statement is the damping ratio of the system. The damping ratio of the system is 3.63. Yeah, percent. Yeah, that should be in percentage. Obviously in percentage.
Percentage, sir. Yes, yes, yes.
Obviously in percentage.
That is why this question I have solved correctly.
No, no.
I have not choose the option D, sir.
Yeah, and these are that's why I specifically told you for the MSQ question you need to look for the particular
Yes, yes.
every solutions. Like get you can have the MSQ question here also. For the exams, for the every week assignment, you will have MSQ type of question. So be careful with the MSQs. Otherwise, you'll get zero. Like in that question. Uh,
Just, sir, here one more thing, sir. Actually, I have joined one more course, finite element method. These two courses, interaction session together at the same timing, sir, 3 to 5.
So you need to, manage these things. What I can say, I cannot say like you should skip your FE class because finite
Yeah,
element also is a heavy course. So,
very. Mhm.
or I cannot say you just skip my class because it's also
Sir,
a
something.
heavy
So,
course.
how to manage this so that we cannot have two lectures at single time, sir?
How to manage it's
I mean, sir, some arrangement should be there no, from your team and their team so that this can be at two time.
no that FE course offered by which IIT?
Actually, IIT, just a moment, sir. IIT Guwahati, I think.
IIT Guwahati itself. Who is
No,
taking
no,
the
no, no,
class?
no, 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 no. Let me see. I'm not sure. I will.
I think we have solved the question. Whatever he just uh, shown, we have solved it, right? And we have get two answers on the last class. Yes or no? Whoever watched the video or go through the sessions, you
Sir,
have the
okay. No, actually, if you are directly in the class, now it will take less time and will get more focus, more attention, sir.
yeah.
And watching video, it is
You just
more,
waste like 2 hours video. It's boring.
No, 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 sir. Actually,
No, it's
direct interaction.
actually it's boring 2 hours video. If you want me to sit and watch this video, I will also say it's boring.
It
Yeah,
is from IIT Kharagpur, sir. FEM is IIT Kharagpur, sir.
yeah, IIT Kharagpur. Then you just stop sharing your screen. Biswajit, okay, Sat Banerjee. Okay, it's also a good course, finite element. And if you don't know the finite element, the proper dynamics is also incomplete. Multibody
Yes,
dynamics is
yes,
also
yes.
incomplete. So, in which course you are, or what are you doing? Like, are you in profession or like you just
So,
stop
sir,
sharing?
actually, I will stop. How to just a moment. Let me go in.
and go there and stop share. Here. Look here. Uh, like one arrow type box is there. Not there. नीचे नीचे देखिए ये नीचे देखिए एक एरो टाइप का बॉक्स है ना एरो हेड टाइप ऑफ बॉक्स उसको क्लिक करना है यू नीड टू
Uh,
एकदम नीचे देखिए मैं देख पा रहा हूँ नीचे ये देखिए
Meet is there. Google Meet is there.
There is a arrow sign.
yeah arrow head sign you cannot do like this arrow head sign no just below your screen yeah there stop sharing just click on the stop sharing yes stop sharing no stop sharing you need to stop it so that I can share the screen because we have already yeah thank you look we have already solved this question whatever your doubt was if you carefully watch the video then you also can able to get the right answer and clearly I have mentioned the percentage
After actually,
look at the question here yeah 3.68 percentage yes or no so we have solved it right uh, can you watch my screen are you
you answered 3.68%, sir. Correctly.
yeah so we have already solved it so whoever watched that video they have entered the correct answer but somehow I think you missed the video we have solved it on the previous class yeah here example number
Yeah,
7
you're right. Yeah, you're right.
okay no issue uh still you have any kind of questions you can directly mail it to my mail id and uh, mm, where are you from Nandal Kumar am I pronouncing it correctly your name Nandal right
Sir, I am from Bihar. Presently, I am in Kerala working in VSSC ISRO, sir.
okay 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 great okay great then yeah for you fe finite element method is very much important and fe analysis I just insist like you learn the process you do some example in MATLAB you do complete analysis of a multibody dynamic system then you will get the flavor of the dynamic and fe at a good time because we are just doing it for the undergrad and postgrad but you need like in a rich level so I will suggest like you should do the course along with the hands-on practice like how to solve a multibody total multibody system within a MATLAB how to get the responses all of these things otherwise like getting the shape function getting the concept of your beam element or your truss element that will not get you that thing what you were looking for okay okay then we'll meet the
Okay.
next session
Okay,
thank
sir.
you thank you
Okay. Thank you. Thank you, sir.
yeah,
Thank you.
if you
Thanks a
still
lot.
have any kind of questions, you can directly mail it to my mail ID p.devasis@iitg.ac.in. Okay, thank you.
Okay, sir. Okay. Okay, fine. Thank you. Have a nice evening
Yeah,
and nice weekend.
yeah, you too also, and all of you too.